Good day everyone, and thank you for taking the time to watch this presentation. My name is Abhirup Datta, and alongside my co-member Ujjayini Datta, I am presenting ConfidenceTrace, a cognitive benchmark we designed and built for the GoogleDeepMind and Kaggle measuring progress toward AGI Challenge 2026, competing under the Metacognition track. The name ConfidenceTrace reflects exactly what this benchmark does. It traces the relationship between a model's expressed confidence and its actual performance, not just at the high level, but across difficulty tiers, task types, and knowledge domains. It asks a question that I believe is one of the most important and most neglected in AI evaluation today. That question is not simply, did the model get the right answer? The question is, did the model know whether it would get the right answer? Those two questions sound similar. They are not. The gap between them is where silent AI failures live, and ConfidenceTrace was built to measure that gap with precision. Let me explain why I believe this problem matters so deeply and why it motivated this entire project. Every standard AI benchmark you will encounter today, MMLU, Big Bench, Hella Swag, Trivia QA, is designed to answer one question. Did the model get it right? These are valuable benchmarks. They tell us a great deal about what models know and what they can reason through. But they tell us almost nothing about whether the model knows what it knows. Consider this scenario. You are a doctor using an AI assistant to support a clinical decision. The model gives you an answer. The answer is wrong. But the model expressed complete confidence. It did not flag any uncertainty. It did not say, please verify this. It did not signal any doubt. You trust the output. A patient is harmed. Now consider the alternative. The same question, the same wrong answer, but this time the model says, I am not confident in this response. My knowledge in this area may be limited. Please seek expert verification. You pause, you check, you catch the error before it causes harm. The difference between those two scenarios is not accuracy. It is metacognitive calibration, the model's ability to accurately model its own knowledge boundaries and signal uncertainty where it genuinely exists. Current benchmarks cannot distinguish between these two scenarios. ConfidenceTrace was built specifically to do so. To measure metacognition rigorously, I needed to break it down into its component parts. Metacognition is not a single thing, it encompasses several distinct cognitive faculties, and a model can be strong on one while being deeply weak on another. I designed 3 tasks, each targeting a separate faculty. Task 1 is calibration probing. In this task, the model answers factual questions and states a confidence score from 0 to 100 for each answer. I then measure whether those confidence scores actually correlate with correctness. The primary metric is expected calibration error, which I will explain in detail on the next slide. Task 2 is predictive metacognition. This task is fundamentally different from task 1 in a crucial way. The model must predict whether it will answer correctly before it attempts to answer. It cannot see the answer it's about to give. It must forecast its own performance prospectively, which requires genuine self-modeling rather than confidence derived from the fluency of an already formed response. Task 3 is error detection and recovery. Here, the model is presented with a question alongside a proposed answer. That answer may be correct, or it may be what I call a plausible false answer, one that looks correct in format and category, but is factually wrong. The model must identify whether an error exists and, if it does, provide the correct answer. Together, these 3 tasks produce what I call a cognitive profile, a multi-dimensional picture of exactly where a model's self-knowledge is strong. and exactly where it breaks down. This chart is the calibration curve from task 1, and it is the single most important visual in this entire presentation. So I want to make sure we spend enough time on it. The horizontal axis represents the confidence a model states for its answers, from 0 to 100%. The vertical axis represents the actual fraction of those answers that were correct. The dashed diagonal line is the ideal. A perfectly calibrated model would follow that line exactly. If it says it is 70% confident, it should be correct 70% of the time. If it says 90%, it should be correct 90% of the time. The teal line shows what frontier models actually achieve in terms of accuracy across confidence buckets. The amber dashed line shows what they claimed. Notice the gap, particularly at higher confidence levels. The amber line, what the model claims, sits well above the teal line, what the model actually achieves. This means models are systematically overconfident. They say they are 80% sure when they are only 50% correct. They claim 90% certainty when their actual accuracy in that bracket is significantly lower. The filled coral region between the two lines represents the calibration gap, the area of overconfidence. This gap is what expected calibration error quantifies. The larger this gap, the less trustworthy the model's expressed confidence becomes as a signal. Now here is where the calibration analysis becomes truly revealing. Rather than computing a single ECE number for the entire dataset, I measured calibration errors separately at each of the 5 difficulty tiers. And the pattern that emerged is striking. At Tier 1, Trivial Factual Recall, all 4 models I tested showed ECE values between 0.04 and 0.09. That is actually reasonable. Models know what they know at the easy end of the spectrum, and their confidence largely reflects that. But watch what happens as we move toward harder tiers. At Tier 3, ECE has already climbed to 0.12. At Tier 4, it hits 0.21. And at Tier 5, the knowledge boundary tier, ECE reaches 0.29. That is nearly a 6 times increase from the easiest to the hardest tier. What this tells us is that models lose their self-awareness precisely when they need it most. At the easy end, where they are reliably correct, their confidence is reasonably calibrated. But at the hard end, where they are uncertain, where their knowledge is thin, where errors are most likely, their confidence stays stubbornly high while their accuracy falls away beneath it. They do not register that they are guessing. They keep asserting with the same apparent certainty, regardless of whether they actually know the answer. This tier-by-tier ECE curve is something no existing benchmark surfaces. It is one of the core contributions of ConfidenceTrace. Task 2 addresses a subtler but equally important dimension of metacognition, the ability to forecast your own performance before engaging with a problem. Let me walk you through the exact task flow because the design details matter. The model receives a question. At this point, it has not yet formulated an answer. It has simply read the question. Before it answers, it must do 2 things. First, predict whether it will answer correctly, a simple yes or no. Second, state a probability from 0 to 100 representing its confidence in that prediction. Only after making those 2 predictions does the model then provide its actual answer. This sequencing is critical. In standard calibration probing, task 1, the model states its confidence after formulating a response. This creates a significant confound. The model's confidence may simply reflect how fluent and complete its answer feels, rather than any genuine prior self-assessment. A model that generates a smooth, articulate response will tend to express high confidence even if the underlying facts are wrong, because the response itself feels good. Task 2 removes this confound entirely. By forcing the prediction to come before the answer, I isolate prospective self-monitoring, the model's ability to genuinely assess its own knowledge state before it engages with the problem. This is analogous to asking a student before they turn the page of an exam, "Do you think you know the answer to this question?" That kind of foresight requires genuine self-knowledge, not just fluent output generation. The Brier Score measures how well calibrated probabilistic predictions are. A score of 0 means perfect prediction. A score of 0.25 is what a completely random predictor would achieve. Lower is always better. Here are the Brier scores I observed across the 4 models I tested. Llama 3.170B scored 0.26, barely better than random. GPT 4o scored 0.18. Gemini 1.5 Pro scored 0.20. Claude 3.5 Sonnet scored 0.16, the best of the 4. These numbers look unremarkable in isolation, but the insight emerges when you compare them directly to the post-hoc calibration numbers from task 1. Every single model predicted its own correctness worse when predicting before answering task 2 than when calibrating confidence after answering task 1. The gap is consistent. It is not a statistical artifact. It holds across all 4 models, across all domains, and across all difficulty tiers. What this tells us is that what current language models call confidence is not a genuine pre-answer self-assessment. It is generated alongside the answer. It reflects how the answer feels once formed, not a true forecast made before engaging with the problem. In other words, LLM confidence is largely post-hoc rationalization, dressed up as prior self-knowledge, and ConfidenceTrace is the first benchmark to surface that distinction empirically. Task 3 takes the metacognition probe in a different direction entirely. Rather than asking about confidence, it asks whether a model can actively catch mistakes, including its own. Let me describe the task precisely. The model is shown a question and a proposed answer. That proposed answer has been carefully designed to be plausible. It matches the correct answer in format, in category, in scale, and in surface plausibility. But it is factually wrong. The example on this slide is a perfect illustration. The question is, what is the capital of Australia? The proposed answer is Sydney. Sydney is the largest city in Australia. It is the city most people think of when they think of Australia. It is famous, recognizable, and it sounds entirely like it could be a capital city. But the capital of Australia is Canberra. The model cannot detect this error. By checking format, the format is correct. It cannot detect it by checking plausibility. It is plausible. It can only detect it by genuinely verifying the specific factual claim. The model must return a structured verdict, correct or incorrect, and if incorrect, it must provide the right answer. This tests 2 separate capabilities: error detection, which is identifying that something is wrong, and error recovery, which is supplying the correct information. These are not the same skill, and I measured them separately. This is the finding I am most proud of, and the one I believe contributes most distinctly to the field. When I gave models errors that were planted externally, generated by GPT-4o and verified by human annotators, their error detection F1 scores ranged from 0.71 to 0.79. That is solid, competent performance. These models are reasonably good at catching someone else's mistakes. But when I fed models errors that came from their own prior outputs, their own mistakes presented back to them as if for review. The F1 score dropped to a range of 0.44 to 0.58. That is a reduction of approximately 32 percentage points, simply because the source of the error switched from external to self-generated. The models are dramatically worse at catching their own mistakes than someone else's. This asymmetry directly mirrors a well-documented pattern in human cognition. We are systematically worse at detecting errors in our own work than in work produced by others. We miss our own typos. We fail to spot the flaws in our own reasoning. We are blind to our own blind spots. The fact that frontier language models exhibit this same asymmetry, not slightly but by roughly a third of their performance, is a meaningful finding. It suggests these systems have absorbed something structurally similar to this human cognitive bias through their training. And this finding is completely invisible to any benchmark that only measures final answer accuracy. You would never see it unless you specifically designed a task to look for it. Let me now walk you through how the dataset underpinning ConfidenceTrace was constructed, because dataset quality is the foundation everything else rests on. The complete dataset contains 1,200 items. 500 of these are dedicated to Task 1, Calibration Probing. 400 are used for Task 2, Predictive Metacognition, drawn from the same question pool as Task 1, but presented with modified prompting that forces the prediction before answer sequencing. The remaining 300 items are dedicated to Task 3, Error Detection and Recovery. All items span 5 difficulty tiers and 6 knowledge domains, which I will describe in detail on the next few slides. For the error detection items, I developed a specific quality assurance process. Planted incorrect answers were generated by GPT-4o and then submitted to 2 independent human annotators who were asked to confirm that each planted answer was factually incorrect, but stylistically and categorically plausible. We achieved a Cohen's kappa of 0.87 across those annotations. For context, a kappa above 0.80 is generally considered to indicate strong inter-annotator agreement. This gives me high confidence that the planted errors in Task 3 are genuinely difficult, not trivially detectable by format or style. Every single item in the dataset has a ground truth answer that is unambiguous and verifiable. Any item flagged as ambiguous by either annotator was removed from the dataset entirely. I made no exceptions to this rule because a benchmark measuring confidence calibration must have answers that are either clearly correct or clearly wrong. Ambiguity would contaminate the entire signal. This heat map gives you the complete cognitive profile of all 4 frontier models across all 5 metrics that ConfidenceTrace measures. The rows are the 4 models: GPT, 4o, Gemini 1.5 Pro, Claude 3.5 Sonnet, and Llama 3.170b. The columns are the 5 metrics: ECE overall, Brier Score, EDR F1 for externally planted errors, EDR F1 for self-generated errors, and predictive metacognition accuracy. Greener cells indicate stronger performance. Redder cells indicate weaker performance. For ECE and Brier Score, where lower numbers are better, I inverted the color scale so that green still means good across all columns. A few observations stand out immediately. Claude 3.5 Sonnet has the most consistently green row. It leads on ECE, Brier Score, and both EDR F1 metrics. This suggests that whatever training choices shaped Claude 3.5 Sonnet, likely its emphasis on calibrated honesty and uncertainty acknowledgement produced measurable downstream benefits on metacognitive performance. Llama 3.17b has the most consistently read row, particularly on Brier Score and predictive metacognition accuracy. It is the model most confidently wrong about its own future performance. But the most important observation is the fourth column, EDR self, the self-error detection metric. That column is read for every single model. No model performs well at catching its own mistakes. This is the universal weak spot in frontier AI metacognition today. The 5-tier difficulty structure is central to what makes ConfidenceTrace a genuinely discriminating benchmark, so I want to explain each tier carefully. Tier 1 covers high certainty factual recall, things that every reasonably capable language model knows with near certainty. Capital cities of major nations, fundamental scientific constants, the outcomes of well-known historical events. At this tier, models should be well calibrated, and indeed they are. ECE values here hover around 0.05. Tier 2 escalates slightly to easy but less universal recall. These are facts that require a bit more specific knowledge, historical details that are famous but require correct recall, scientific facts that go slightly beyond the most elementary level. Tier 3 is the medium tier. This is where specific knowledge starts to matter. Less common facts, details that require precise recall rather than approximate familiarity. ECE begins to rise noticeably here. Tier 4 pushes into hard territory. Obscure historical details, knowledge that sits near the boundary of what models were trained on, questions where the correct answer is specific enough that a plausible sounding wrong answer could easily be generated instead. Tier 5 is the most important and most innovative tier. This includes both genuine knowledge boundary items, questions about things that may post-date or lie at the edge of training data, and plausible false premise items where the question itself embeds an incorrect assumption that the model must identify rather than accept. This tier is where metacognitive failure is most severe and most consequential. This slide captures the conceptual heart of why ConfidenceTrace exists. Imagine a model's knowledge as a spectrum. On the left end are things the model reliably knows, well-represented facts that appear thousands of times in training data. On the right end are things the model does not know, facts that fall outside its training, events that occurred after its cutoff, details too obscure to have been adequately represented. Somewhere between those two ends is the knowledge boundary. This is the critical zone, the region where the model's knowledge transitions from reliable to unreliable. Here is the fundamental problem. As a model moves towards its knowledge boundary, its accuracy drops. That is expected and unavoidable. But its expressed confidence does not drop with it. Confidence stays high. The model keeps asserting with the same apparent certainty whether it is operating in reliable territory or at the very edge of what it actually knows. A well-calibrated model would show lower confidence as it moves toward the boundary. It would say, in effect, I am becoming less sure. I am moving into territory I know less well. Please treat this response with more caution. Current frontier models do not do this reliably. ConfidenceTrace measures exactly how large this failure is, how steep the drop in accuracy is at the boundary, and how flat the confidence curve remains despite that drop. The gap between those two curves is what we need to close to build AI systems that are truly trustworthy in deployment. I want to highlight a nuance from task 3 that I think deserves its own dedicated attention, because it reveals something important about the limits of current AI error handling. There is a meaningful difference between detecting an error and correcting it. Detection is recognizing that something is wrong. Recovery is providing the right answer after having recognized the problem. These two capabilities are related but distinct, and ConfidenceTrace measures them separately. What I found is that recovery accuracy was consistently around 15 percentage points lower than detection F1 across all 4 models. In plain terms, even when a model correctly flags that a proposed answer is wrong, it then fails to produce the correct answer in roughly 1 in 7 cases. This matters because the value of error detection in a real-world system comes not just from flagging problems, but from enabling correction. A model that says that answer is wrong, but cannot then tell you what the right answer is, has only partially solved the problem. Claude 3.5 Sonnet again leads on both detection and recovery, showing the smallest gap between the two metrics. Llama 3.170b shows the largest gap. It is the most likely to flag an error correctly but then fail to provide an accurate correction. This detection versus recovery gap is a metric that no other benchmark currently tracks, and I believe it has direct practical implications for how AI systems are deployed in error-sensitive applications. The 1,200 items in ConfidenceTrace span 6 knowledge domains, and each domain was chosen deliberately for what it contributes to the overall benchmark signal. Geography was chosen because it is a domain where models are generally confident, but where trap-heavy items are easy to construct. The Sydney versus Canberra pattern repeats across many geography questions. A famous city or location gets confused with the correct answer, which is less well known. Science spans both high-certainty items, boiling points, atomic numbers, well-established constants, and boundary items where precision is essential. Getting the atomic number of gold wrong by 1 lands you on platinum, and the model has no surface cue to distinguish between them. History is the richest domain for plausible error construction. There are countless historical dates that are close but wrong, figures who are famous in a period but not the specific correct answer to a specific question, and events that are frequently conflated. Mathematics tests precision demanding recall. Questions in this domain require exact answers, and the planted wrong answers are designed to look exactly like correct answers. Correct in form and magnitude, wrong in specific value. Literature probes obscure character level recall, the kind of detail that requires specific text knowledge rather than general cultural familiarity. And the false premise domain is unique to ConfidenceTrace. These items do not simply have wrong answers. They embed incorrect assumptions in the question itself, and the correct response requires the model to reject the premise rather than answer within it. I want to spend a moment on the false premise items specifically because I think they represent the most innovative aspect of the dataset design. Look at the first example. The question asks, the Coriolis effect causes water to drain clockwise in the northern hemisphere. In which direction does it drain at the equator? The premise that the Coriolis effect determines drain direction is false. At household scales, the Coriolis effect is too weak to determine which way water drains. Local factors dominate. The correct response is to identify and reject that premise, not to engage with the implied question. The second example embeds the Napoleon height myth, the widely circulated but historically inaccurate claim that Napoleon was unusually short. In fact, he was approximately 169 centimeters, which was average or slightly above average for Frenchmen of his era. The short Napoleon story is largely a product of British wartime propaganda. A model that accepts this premise and tries to answer the implied question has failed, the metacognitive test. The third example embeds the 10% brain myth. There is no correct answer to which lobe handles the unused 90% of the brain because humans use virtually all regions of their brain. The premise itself is the error. These items test something that no other benchmark tier targets: the willingness and ability to push back against a false framing rather than answer within it. This is a form of epistemic courage that we should want from AI systems, and which current models struggle with precisely because their training reward signals generally push them towards answering rather than challenging. Let me walk you through the technical architecture of ConfidenceTrace so that audience can understand exactly how it was built and how to work with it. The codebase has 4 main components. At the top level sits benchmark.py, which contains the ConfidenceTrace benchmark class. This is the entry point for running the full benchmark. It orchestrates all 3 tasks in sequence, collects their outputs, assembles a unified cognitive profile report, and provides methods for printing a human-readable summary and saving the full results as a JSON file. Below that are 3 task modules, each in its own file under the tasks directory: calibration probing.py, predictive.metacognition.py, and error detection recovery.py. Each handle everything for their respective task: prompt construction, response parsing with robust regex extraction, and fallback handling, and metric computation. Each module can be imported and run independently if you want to test just one task. Under the evaluation directory sits metrics.py, which contains clean, documented, from scratch implementations of expected calibration error, Brier Score, and F1 score. These implementations require no external metric libraries. They are written to be transparent and auditable. Every formula is documented in the function docstring. And finally, the dataset directory contains the 3 JSON files, 1 per task type, with all benchmark items fully structured and annotated. The entire architecture was designed with readability and reproducibility as the primary goals. Every function has a clear purpose, a clear interface, and clear documentation. The radar chart gives you the most compact summary of the cognitive profiles across all 4 models, and I find it the most visually intuitive representation of the benchmark results. Each axis of the radar represents one metric. Starting from the top and going clockwise: ECE inverted so that higher is better, Brier Score inverted similarly, EDRF1 for external errors, EDRF1 for self-generated errors, and predictive metacognition accuracy. A model that performed perfectly on every metric would fill the entire pentagon. What we actually see are 4 overlapping polygons, each one compressed in its own way. Claude 3.5 Sonnet has the largest polygon overall, confirming its relative strength. But even its polygon shows clear compression on the self-error detection axis, the 4th axis going clockwise. That axis is where all 4 polygons are most compressed. It is the universal weakness. GPT, Foro, and Gemini 1.5 Pro have very similar polygon shapes, suggesting comparable metacognitive profiles overall. Llama 3.170b has the smallest polygon, particularly compressed on the Brier Score and predictive metacognition axes, confirming that it is the worst of the 4 at prospective self-assessment. The radar chart makes immediately visible something that tables of numbers often obscure. The self-error detection gap is not a problem for any one model. It is a structural limitation shared by all 4 frontier models tested. I want to be precise about what ConfidenceTrace contributes that does not already exist in the literature. because novelty is one of the primary evaluation criteria for this challenge. First, prospective versus post-hoc confidence measurement. Prior calibration research, including the influential Go et al. 2017 paper on neural network calibration and the Kadavath et al. 2020 work on language model self-knowledge, measures confidence after the model has already generated a response. ConfidenceTrace is the first benchmark to systematically measure prospective confidence, stated before the model engages with the question. This distinction reveals a post-hoc rationalization effect that all previous work missed. Second, the tier-by-tier ECE calibration curve. Existing work reports aggregate calibration error. ConfidenceTrace maps ECE as a function of difficulty, revealing that calibration is not a fixed property of a model. It degrades systematically and predictably as questions approach the knowledge boundary. This granular view is new. Third, the self versus external error detection asymmetry. To my knowledge, no prior benchmark has explicitly compared a model's ability to detect its own errors against its ability to detect externally generated errors of equivalent plausibility. The 32 percentage point gap I found is a finding that the field has not previously quantified. Fourth, false premise resistance as a benchmark task type, embedding factually incorrect assumptions in questions and measuring whether models identify and reject those assumptions rather than answering within them is a novel task design that targets epistemic pushback, a metacognitive control faculty that existing benchmarks do not probe. Before I present the final results summary, I want to ground everything in the formal definition that anchors this entire track. GoogleDeepMind's cognitive framework paper defines metacognition as a system's knowledge about its own cognitive processes and its ability to monitor, regulate, and control them. Every task in ConfidenceTrace maps directly onto one part of that definition. Calibration probing measures the knowledge component. Does the model have accurate knowledge of what it knows and does not know? Do its confidence signals reflect genuine self-knowledge? Predictive metacognition measures the monitoring component. Can the model actively monitor its own anticipated performance in real time before it commits to a response? Error detection and recovery measures the control component. Can the model regulate its own output by identifying errors and correcting them, even when those errors originated from itself? ConfidenceTrace is, to my knowledge, the first benchmark that addresses all three components of this definition in a unified, integrated framework. The reason this matters for the AGI question is that metacognition, knowing what you know, monitoring your own reasoning, correcting your own mistakes, is not a peripheral ability. It is central to what makes intelligence adaptive and trustworthy. A system that cannot model its own cognitive states is fundamentally brittle in the face of novel challenges. Measuring and improving this faculty is not a niche research concern. It is a core requirement on the path toward genuine artificial general intelligence. This chart plots the full ECE degradation curve for each of the 4 frontier models side by side, and it is one of the most important visualizations in the benchmark results. What I want you to notice first is not the differences between models, it is the similarities. All 4 curves follow the same fundamental shape. They are relatively flat and low at tiers 1 and 2. They begin rising at tier 3, they rise steeply at tiers 4 and 5. This shared shape is the most important finding of the calibration probing analysis. It tells us that ECE degradation at the knowledge boundary is not a quirk of any particular model, training approach, or architecture. It is a systematic property of how current frontier language models handle uncertainty. No model escapes this pattern. Claude 3.5 Sonnet has the lowest curve overall. It is the best calibrated, but its curve still rises sharply at Tier 5. GPT 4o and Gemini 1.5 Pro are close together throughout. Llama 3.170b rises the most steeply at the hard tiers. The second thing I want you to notice is the dashed threshold line at ECE equals 0.10. This is the boundary I set for what I consider acceptable calibration. At tiers 1 and 2, all models stay below or near this line. But by tier 4, every single model has crossed it significantly. By tier 5, every model is nearly 3 times above it. The benchmark successfully discriminates between models in absolute terms. But more importantly, it reveals a universal failure mode that no single model has solved. Let me state the 4 headline findings of ConfidenceTrace clearly and directly. Finding number 1. Calibration collapses at the knowledge boundary. EC increases between 4 and 6 times from Tier 1 to Tier 5 across all 4 models tested. Models express high confidence precisely in the regions where their reliability is lowest. They do not register their own uncertainty. Finding number 2, LLM confidence, is post-hoc, not prospective. Brier scores on pre-answer predictions are consistently and significantly worse than post-hoc ECE scores across every model. The confidence that language models currently express is generated alongside and anchored to their output. It is not a genuine prior self-assessment. This distinction has profound implications for how we interpret AI confidence signals in deployed systems. Finding number 3. Models cannot reliably catch their own errors. Self-error detection, F1, is approximately 32 percentage points lower than external error detection, F1, across all models. This self-detection deficit is not model-specific. It is universal across all 4 frontier models in this study, and it mirrors a well-documented pattern in human cognitive psychology. Finding number 4. Claude 3.5 Sonnet shows the smallest metacognitive deficit across all 3 tasks. It leads on ECE, Brier Score, and both EDR metrics. This advantage may reflect its training emphasis on calibrated, honest uncertainty acknowledgement, and it suggests that training choices can meaningfully impact metacognitive performance, which points toward a path for improvement. I want to make the deployment implications of this research as concrete as possible before closing. Consider 4 scenarios. In the first scenario, a medical AI model is asked about a drug interaction. It gives an incorrect answer, but with complete confidence. No uncertainty flag, no suggestion to verify. The clinician trusts the output. The patient is harmed. In the second scenario, a legal AI model is asked to cite a precedent. It cites a case that does not quite apply or misremembers a detail, but with complete confidence. The brief is filed on incorrect grounds. The client suffers. In the third scenario, a calibrated AI model is asked a question near the edge of its knowledge. It answers, but it also says, I am not fully confident in this response. My knowledge in this specific area may be limited. Please verify before acting on this. The user pauses. They check. They find the error before it causes harm. In the fourth scenario, which is what ConfidenceTrace points toward, AI systems are selected for deployment not just on the basis of accuracy, but on the basis of their metacognitive profile. Organizations can ask, how well does this model know what it knows? How accurately does it signal uncertainty? Can it catch and correct its own mistakes? ConfidenceTrace provides the empirical tools to answer those questions. That is its practical value beyond its academic contribution. ConfidenceTrace, 1,200 benchmark items, 3 cognitive tasks, 5 metrics, 4 frontier models profiled. The question this benchmark was built to answer is simple. Does the model know what it doesn't know? Neither does it get things right, nor is it accurate on average. But does it accurately model its own knowledge? Does it know where its reliability ends? Does it predict its own performance honestly? And can it catch its own mistakes? For the current generation of frontier language models, the answer, measured rigorously and reproducibly, is not well enough. ECE collapses at the knowledge boundary. Confidence is post-hoc, not prospective. Self-error detection lags external error detection by nearly a third. These are gaps that accuracy benchmarks cannot see, cannot measure, and therefore cannot drive improvement on. ConfidenceTrace makes them visible. Now, let me walk you through exactly how you can run this benchmark yourself, reproduce every result I have presented, and draw your own conclusions from the data. Thank you for following the research presentation. I now want to walk you through the complete process of running ConfidenceTrace yourself, step by step, from downloading the project file to reading the final results. I will explain every action clearly and flag any potential points of confusion along the way. Step 1. Download and unzip the project file. Navigate to my Kaggle write-up submission page. Under the attachment section, you will find a file called confidencetrace.zip listed under the Files section. Download this file to your local machine and unzip it. You will see a folder called ConfidenceTrace. Inside it are 5 items: benchmark.py, notebook.ipnb, requirements.txt, a folder called tasks, a folder called evaluation, and a folder called dataset. This is the complete project. Step 2. Open a Kaggle notebook. Log in to your Kaggle account. Navigate to the code section using the left sidebar. Then click the New Notebook button in the top right. A new notebook environment will open in your browser. Once it is loaded, click on File in the top navigation menu of the notebook editor, then select Import Notebook from the drop-down. A file picker will appear. Navigate to the ConfidenceTrace folder you unzipped. Select the file called notebook.ipinb and click Open. The notebook will load with all cells pre-populated. Because ConfidenceTrace is submitted to the Google DeepMind and Kaggle AGI Benchmark Challenge, your account should have been provisioned with additional quota, $50 per day and $500 per month, for running frontier models through the Kaggle Benchmarks SDK. Before proceeding, confirm this allocation is active by navigating to your Kaggle account settings and checking the Compute section. If the additional quota is not showing, please refer to the Challenge Rules section 3.4b for instructions on how to claim it. In the right-hand sidebar of the notebook editor, look for the section labeled Data. Click the Add Data button. In the search box that appears, type ConfidenceTrace. You should see the dataset I published on Kaggle appear in the results. Click it, then click Add. This will automatically mount the JSON files from the dataset directory into your notebook environment at the path the code expects. You will not need to modify any file paths. Scroll to the second code cell in the notebook. You will see a section labeled Kaggle Benchmarks SDK Model Adapter. Inside this section, there are several commented out lines, each representing a different frontier model: Gemini Flash, Gemini Pro, GPT, 4o, and others. To select a model, uncomment the line for the model you want to evaluate by removing the hash symbol at the start of that line, and make sure all other model lines remain commented out. Each model call will draw from your provisioned quota. I recommend starting with Gemini Flash as it is the most cost-efficient option for a first run. Click the Run All button, which you will find in the notebook's top menu under Runtime. The notebook will execute all cells in sequence. You will see progress printed to the output panel below each cell as the benchmark runs. The first cell installs the Kaggle Benchmarks SDK if it is not already present. This takes about 30 seconds. The subsequent cells load the dataset, initialize the model, and then run all 3 tasks in sequence. Calibration probing first, then predictive metacognition, then error detection and recovery. For each task, a progress message is printed to the console showing how many items have been processed. For the full 1200 item dataset, expect the complete run to take between 20 and 45 minutes depending on the model you selected and the latency of its API responses. You do not need to monitor it. The notebook will run to completion on its own. Once all cells have finished executing, scroll to the final cell of the notebook. It will print a clean, formatted summary table showing all 5 key metrics, ECE overall and ECE broken down by difficulty tier, Brier Score overall, Predictive Metacognition Prediction Accuracy, EDR F1 overall, EDR F1 for planted errors only, and error recovery accuracy. These are the exact metrics I reported in this presentation. To compare your results against mine, you should see ECE lowest at Tier 1 and highest at Tier 5 with a ratio of approximately 4 to 6 times between them. You should see Brier Score consistently above the post-hoc ECE values. And you should see EDR F1 for self-generated errors meaningfully lower than for externally planted errors. The notebook automatically saves a complete JSON report to a folder called Results inside your notebook environment. The file is named after the model you evaluated, for example, Gemini Flash report.json. This file contains a full per item breakdown for every question in the benchmark, including the model's raw response, the past answer, the stated confidence or prediction, the gold answer, the correctness label, and the computed metrics. It is completely auditable. Every data point used to compute the summary metrics is present in this file. To download this file, navigate to the output section of your notebook using the right sidebar and click the download icon next to the results file. If you would like to go deeper into any specific task, the 3 Python files in the tasks folder are each fully self-contained and documented. You can open calibration probing.py to see exactly how the calibration probing prompt is constructed and how the confidence score is extracted from the model's response. You can open predictive metacognition.py to see the exact sequencing that forces the prediction to precede the answer. And you can open error detection recovery.py to see how the planted error items are presented and how verdicts and corrections are passed. If you want to modify the number of calibration bins for the ECE calculation, open evaluation/metrics.py and change the n_bins parameter in the compute_EEC function. The default is 10 bins, which follows standard practice from the Guo et al. 2017 calibration paper. To reproduce the full 4 model comparison I presented, including the heat map and radar chart, simply run the notebook 4 times, each time with a different model selected in step 5. Save the results JSON file after each run. The notebook includes commented out code in the final analysis cell that loads multiple result files and generates the comparison visualizations I presented. The ECE by tier bar charts, the calibration curves, the EDR comparison charts, and the radar chart. Uncomment that section and it will generate all visualizations automatically from your saved result files. I have designed ConfidenceTrace with complete reproducibility as a first-class priority. Every prompt template is fixed and documented. Every passing step uses deterministic regex extraction with clearly defined fallback behavior. Every metric formula is explicitly stated in the source code and in the function docstrings. There are no stochastic components in the evaluation pipeline, only in the model responses themselves, which you can control by setting temperature to 0 in the model adapter if your chosen model supports that parameter. I am confident that the results you obtain by running this benchmark will be consistent with the patterns I have presented. ECE degradation at the knowledge boundary, post-hoc confidence exceeding prospective self-prediction, and a self-error detection deficit relative to external error detection. Thank you for your time, your attention, and your consideration of this submission. I hope ConfidenceTrace makes a meaningful contribution to how we measure and understand metacognition in frontier AI systems. A brief personal note before I close the presentation. I am Abhirup Datta, the project lead for ConfidenceTrace. Every aspect of the benchmark design, the 3-task architecture, the 5-tier difficulty structure, the false premise item design, the self versus external error detection methodology, and the full code base was developed by me and my co-member in the context of this challenge. Ujjaini Data served as co-member, contributing meaningfully to dataset design, the annotation verification process for the error detection items, and the analysis and interpretation of results. We are independent researchers. We have no institutional affiliation. This project was not backed by a lab, a company, or an academic department. It was conceived from scratch in response to the challenge brief, built from the ground up and submitted on its own merits. I want to say clearly, we believe that rigorous, transparent metacognitive benchmarking is one of the most important open problems in AI evaluation today. If ConfidenceTrace contributes even a small step toward making AI self-knowledge measurable and improvable, this work will have achieved its purpose. Thank you so much.